Hi folks, we're going to take a look at a couple of questions from page 575 involving derivatives of natural logarithmic functions. Okay, so in this first in here, they want us to find the derivative of the function given. So here s prime at t is going to be equal to, now here I've got a quotient, so I'm going to be using the quotient rule. The numerator and denominator are both fairly simple functions. So start with the derivative of the numerator. Derivative of e to the t is just e to the t. Of course, here we're taking all the derivatives with respect to whatever variable we have, in this case here, t. All right, and then we multiply that by the denominator function, ln t, okay, minus the numerator function, ln t, e to the t, and then times the derivative of the denominator function, and the derivative of ln t is 1 over t, okay? And then all that over the square of the denominator function, so ln t squared. Okay, and we can just leave our answer here, and it could very well be that the question asks you to give the answer unsimplified, or I might as well just simplify it a little, see how far I can go. Okay, so I'll stick with the numerator here. I'll see that there's a fractional part of the second expression, so I'll subtract these using a common denominator of t. So this expression does not have the denominator of t, so I'll multiply that there. So t e to the t ln t minus e to the t all over t. Okay, and then still the denominator squared. All right, here when I'm dividing by ln of t squared, okay, it's like multiplying by 1 over ln t squared. So this, I'll just go into the denominator there. And if I want to, I guess I can factor out the e to the t. Okay, I don't know if that's actually simpler, but you know, one way of writing it out. So what are we left with here? We're left with t ln t minus 1, and then here we have t times ln t squared. Okay, so just to recap this one, okay, recognize this as a quotient, so you're going to use the quotient rule, and then of course you need to know the derivatives of these two basic functions. E to the t, its derivative is just itself, and derivative of ln is just 1 over the variable. All right, let's move on to 6b. So here they want us to determine when the derivative is equal to 0. So in other words, we're looking for some of the critical numbers here. So let's start by taking the derivative of this function. So the derivative is going to be given by, now here I'm going to use the chain rule. So think of this as u to the 1/3. So when I take the derivative, it's going to be 1/3 u, which is this whole thing, ln x plus 2x, to the negative 2/3, because I'm subtracting by 1. Okay, and now I take the derivative of the inside function. So derivative of the outside function, x to the 1/3, and then the derivative, multiply that by the derivative of the inside function. So again, derivative of ln x is just 1 over x, and then of course derivative of 2x is just going to be 2. All right, so let's simplify here. So again, if it asks you, well, I guess we do want to find when it's equal to 0, so it does make sense to simplify this first. Okay, so I want this to be equal to 0. So this whole component is going to go into the denominator. Okay, I've got the 3 in the denominator, so I have 3 ln x plus 2, plus 2x to the 2/3. Okay, this is the negative exponent. And now let me simplify this top part. So again, common denominator of x. So I'm going to have 1 plus 2x over x. And again, this just comes into the denominator. Again, if you need to think about it, dividing by this expression is like multiplying by its reciprocal. So still stays in the denominator. So I've got 1 plus 2x all over 3x times ln x plus 2x to the 2/3. But in the end, since I'm determining when this expression is equal to 0, I just need to focus on the numerator, because the fraction can only be equal to 0 if the numerator is equal to 0. So that means that 1 plus 2x has to be equal to 0, and so x is going to be equal to, bring it to the other side, negative 1 divided by 2, x has to be equal to negative 1/2. Okay, and if I just kind of stopped there and just said, okay, I solved the problem, but the issue here is that negative 1/2 is what made this denominator equal to 0. This numerator equal to 0. But of course, I have to remember that I'm dealing with this function, which has part of it, which is not quite as nice as, you know, the polynomial or the exponent 1/3. Okay, this function has a domain of x greater than 0, because you can't take the logarithm of something equal to 0 or less than 0. Hence, there's actually no solution. Okay, and why? Because ln of -1/2 does not exist. Okay, so while this did solve the numerator being equal to 0, it's actually not a valid input into the original function. Okay, so in this case here, we actually have no solution. All right. So again, just to recap here, first thing was to recognize that we needed to use the chain rule. So take the derivative of the outside function, which is x to the 1/3, okay, and then multiply that by the derivative of the inside function. Again, we had to use the derivative of ln x. Do my simplification, ended up with a single fraction. Numerator needed to be equal to 0. Problem was that solution was not in the domain of the original function. So in the end, there was actually no x value that makes the derivative equal to 0. All right, that's it for these.